Okay, let's move on with our chapter on the electronic spectra. In the last class, we have started to look at what happens to terms in octahedral ligand field. And we've seen that the terms split into additional states, and the energy of the states now depends on how strong the ligand field is. So that can be plotted in a correlation diagram, and we've discussed the Tanabe-Sugano diagram of a D2 octahedral complex as an example of a correlation diagram. And we have determined that from the ground state, there are 3 possible transitions. So the ground state is in this case a triplet state. It's a triplet T1 state. So according to the selection rules, there are only transitions into other triplet states allowed. So that means that we can excite from the triplet ground state to this triplet state here, as well as this triplet state over there, and finally we can also excite to a third triplet state. Okay. So now, what about the other electron configurations and Tanabe-Sugano diagrams of other electron configurations? So let us look, for instance, at the D3 electron configuration for an octahedral complex. So you see that the ground state is in this case a quartet state. So how can we understand that this is a quartet state? Well, first of all, let us look at the electron transitions. So we can only have electron transitions from this quartet state into other quartet states. So the first electron transition would go into this quartet state here. Then we have another quartet state over there. And finally, we have a third quartet state over here. So these are all the electron transitions possible from the ground state. So now to the question, how can we understand that our ground state is actually a quartet state? And we can understand this from the fact that in the D3 electron configuration, we would have 3 unpaired electrons in the T2G orbitals, and according to this, 3 times a half would be 3 halves, and then 2 times 3 halves plus 1 is equal to 4. Okay. Now, of course, we have to keep in mind that this state, as we have depicted here, is only one of a number of microstates that can that are part of this term. But this state here would be the microstate that would basically determine the spin multiplicity. Okay, so now what about the D4 electron configuration for an octahedral complex? So you see, in this case, our diagram looks more complicated. You see that we have this horizontal line here. And that is because for D4 octahedral complex, we can have high spin and low spin complexes. So below a certain ligand field strength, our complex is a high spin complex, but above a certain ligand field strength, our complex is a low spin complex. And that means that our ground term must change as we switch from a high spin complex to a low spin complex. So you see from this diagram here that at low ligand field strength, our term is a quintet term. It's actually a 5e term to precise. And up to this ligand field strength, which would be approximately 2.8b, this term would be our ground term. However, above this ligand field strength, we would switch from a high spin to a low spin complex, and then a triplet T1 term would be our ground term. Okay, now what about the electron transitions possible? So if we have a high spin complex, then we can only have, so now it's the other way around. So let us first look at, let us first understand why for a high spin complex, we have a quintet term as the ground state. So again, we can derive this fairly easily from this orbital diagram. So for a small delta O, okay, we write all the electrons spin up. The spin pairing energy is not being overcome. And then what is the spin multiplicity? Well, we have 4 unpaired electrons. So that means that S is 4 times a half, which is equal to 2. And then 2S plus 1 is equal to 5. Note again that this only represents one of several microstates, but this microstate, as depicted here, is the one that determines the quantum number capital S. Okay, it's the microstate with the highest MS value, which defines S. So now, as we increase delta O, we can switch from a high spin complex to a low spin complex. So that means that this electron here is spin paired and moves down into this EG orbital. So now we have only 2 electrons left that are unpaired. And then 2 times a half is equal to 1. And 2S plus 1 then gives equal to 3. And that explains why our ground term is a triplet term. And now let us look at the electron transitions, first for high spin complex. So the ground state for our high spin complex is a quintet state. So we can excite only into other quintet terms. Okay, so we see that we have another quintet term here. So are there any other quintet terms? The answer is no, there are no other quintet terms. So that is our only possible electron transition here. If we have a low spin complex, then a triplet term is our ground term, and we can excite only into other triplet terms. Okay, so we see that we have here an additional triplet term, this 3e term. Okay, and there we have another triplet term, and we have even here another one, okay, which is also a triplet term. So no other triplet terms. It is single term, this quintet term into which we cannot excite. So a low spin complex, we would therefore expect 3 absorption bands due to 3 possible electron transitions. Okay, so now we can just build on this and go from the D4 to the D5 electron configuration. So did I overlook something? So we have here this triplet term, and we have the second one, the third one, and the fourth one. So actually, we have even 4, and that makes 4 electron transitions possible. Okay, now what about the 5 octahedral complex? So also for the 5 octahedral complexes, we can have high spin and low spin complexes. So in case of a high spin complex, we have a 6th term as a ground state. And in the case of a low spin complex, we have a doublet term as the ground state. Again, let us understand why this is a 6th term and this is a doublet term. So for the electron configuration D5, we have a high spin complex. Then we can fill 3 electrons unpaired into the T2G orbitals and 2 other unpaired electrons into the EG orbitals. Okay. Now, when we again count the spin multiplicity, then S is 5 times a half. So that gives 5 halves. And then 2 times 5 halves plus 1 is equal to 6. Okay, explaining why this is 6th term. Again, keep in mind that this is not the only microstate possible. There can also be other microstates that belong to this term. Okay, but this is the microstate here that defines the quantum number S. Okay, so now what about a low spin complex? So in a low spin complex, we minimize the number of unpaired electrons. So these 2 electrons go into these T2G orbitals, and that leaves this electron here as the only unpaired electron. So what is the quantum number S? Well, the quantum number S is in this case 1 times a half. Okay, so this is actually just a half. Okay, that's not 1. Okay, that's just a half. I'm sorry about this mistake. And then 2 times a half is 1, right? Plus 2, which plus 1, which is equal to 2. Okay, so this explains why this quintet term here. Sorry, doublet term here. All right, so now what electron transitions are allowed? Let's first look at the high spin complex. Can any one of you tell me how many electron transitions are being allowed for a high spin complex from the ground state?
Zero.
Sorry?
Zero.
0, correct. Because there's no other 6th state. Okay, so all the other states here that you can see are not 6th states. So that means really for D5 high spin, the D5 high spin complex should be should actually be colorless. Okay, and when you think about an example, then for instance, magnesium 2 plus in water, a hexaacyl magnesium 2 plus ion in water is a D5 high spin complex. And when we make a solution of, for instance, so not magnesium, but manganese. Look at a solution of manganese sulfate in water, then it's pretty much colorless. However, it has a very, very slightly pinkish touch. Yeah, it's very, very slightly pinkish, especially at higher concentration, and that is because also the spin selection rule does not hold entirely strictly. Okay, so at a very, very low probability, there are still transitions allowed from the 6th state into other states, violating the spin selection rule, but only at a very, very low probability, and that means that the color is only very, very light. Okay, it's only very, very lightly pinkish. Okay, now as we go from the high spin complex to the low spin complex, we go from the sixth state to this doublet state. And now the number of electron transitions allowed will depend on, well, how many other doublet states we have. So this is a quartet state, this is a sixth state, this is a quartet state, but we see the next doublet state is actually here. Okay, so that should be our next possible electron transition. So this one here, this 2e is also a doublet term. Okay, so therefore we have a second electron transition possible. And then we see here that this one, the 2a1 is also a doublet state. And that will define our third electron transition. But other than that, we do not have any more doublet state. This is a quartet term, 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 and this is a quartet term. So in this case, we have 3 electron transitions for a low spin complex. Okay, now let's go from a D5 to a D6 octahedral complex and just do the same. So for D6, high spin and low spin is common. So for the high spin complex, we have a quintet term as the ground state. For the low spin complex, we have a singlet term as the ground state. Again, let us understand this by looking at the orbital diagrams. So for a high spin complex, we maximize the number of spins. We can fill 1, 2, 3, 4, 5 electrons spin up into the orbitals, but then the 6th one must be paired and be placed into the T2G orbital. Okay, so that leaves 1, 2, 3, 4 unpaired electrons. Okay, so now what is capital S? Well, it's 4 times a half, well, that is 2. And then 2 times 2 plus 1, well, that is 5, explaining why this term is a quintet term. Again, I want to stress that this is only 1 microstates out of several microstates belonging to this term, but this microstate determines capital number S, and therefore it determines the spin multiplicity. Okay, so now let's go to a low spin complex. And by going to a low spin complex, we must pair the spins. So these 2 electrons that are spin up must go into the T2G orbitals and reverse their spin so that the Pauli principle is not violated. So now we see that we do not have any unpaired electrons, and accordingly we have a singlet term. So 0 times a half, well, that is 0, and 0 plus 1, that is 1. Again, I made here a typo. So 0 plus 1 is not 0, but 1, and that explains why this is a singlet term here. Okay, now how many electron transitions are possible? So here we have a quintet term, so we can only excite into other quintet terms. So how many other quintet terms do we have? Well, we have this one here. Okay, we extrapolate this line. Yeah, then that gives this quintet term here over there. And that's actually the only one. There are no other quintet terms but this quintet term. Yeah. And if we go to a low spin complex, then we can excite from this singlet term to this other singlet term, and there are no other, or no, there's this singlet term here. Okay, so that is also possible. And we have this singlet term here. It should actually also be possible. And I don't understand right now why there's no line. There should actually be also a line for this, and apparently this line has been overlooked. And by closer inspection, I even see a third A1 term here. So yeah, apparently I overlooked this, so we have to actually add the transition into this 1E term here, and also the transition into this 1A2 term here. So this number needs to be corrected, and there needs to be 2 additional possible transitions. And there's here even another single term, which I just certainized. I don't know why I did not see these. Okay, I apologize. So we need to correct this. Okay, now let's go to the D7 octahedral complex. So for the D7 octahedral complex, we have here the quarter term for the ground state of the high spin complex, and here the doublet term for the low spin complex. So we have here for the high spin 3 unpaired electrons. So that means that S is 3 times a half, which is 3 halves. Okay, and then 2 times 3 halves plus 1, that is equal to 4. So this explains this 4. And now for the low spin version, we have to pair these 2 electrons. Or we want to pair these, but we can only pair 1, because after, well, the first pairing, this electron is being left over unpaired. And that means that now S is 1 times a half, which is a half, and 2 times a half plus 1 is equal to 2. So now, what about the number of electron transitions? Well, we have here quartered states, so we can excite into other quartered states. So how many other quartered states do we have? Well, this is a doublet, this is a doublet, this is another quartet. Okay. So we should be able to excite into this quartet state. That is exactly what we can do. And we see that there's here another quartet state, okay, into which we can excite, whereby this arrow here refers to the third possibility of this quartet state. Okay, so this arrow here refers to this quartet state over there. Okay, good. So here we have a doublet. So now how many other doublet terms do we have? This is a quartet. This is a doublet. Okay, so we can excite here. This here is also a doublet. Okay, so we can excite here. This is a quartet, this is a quartet, but this here is another doublet. And again, this is missing, and I don't know why this is missing. And here is even another doublet. And I apologize for these mistakes. So we have to add more transitions here as well. So because this is a doublet and this is another doublet. All right, so now let's go to the D8 electron configuration. So for the D8 electron configuration, things are being simpler again, because for the D8 electron configuration, we have only, we cannot have high and low spin complexes. So our diagram looks simpler again. We only need to understand why our ground term here is a triplet term, and then look at what electron transitions are being allowed. All right, so let us answer the first question. We have in this case 8 electrons. So here we have 6, and here we have 2, that gives 8. So we have overall 2 unpaired electrons. So 2 times a half, that is not 2, but 1. So again, I apologize that this is wrong. So 2 times a half, that is 1. And then 2 times 1, well, that is 2. Okay, plus 1 gives 3. Okay, so that explains why this is a triplet term. And now let us understand which electron transitions are allowed. So how many other triplet terms do we have? Well, this is a singlet term. This is a singlet term. And this here is a first triplet term. So that defines the first electron transition. Here, this is another triplet term, which defines the second electron transition. And that is a singlet, that is a singlet, but that is another triplet, okay, which defines the third electron transition. This is a singlet, this is a singlet, and this is also a singlet. Okay? So therefore, we have 3 electron transitions. So luckily, at least, this is right. Okay. Now, let us consider a last possible type of electron transition, which is called the charge transfer transitions. So thus far, we have only considered electron transitions from between the d orbitals, which are called dd transitions. So from a T2G to an EG orbital. But there are other transitions possible, which are not dd transitions, and they are called charge transfer transitions. So it becomes apparent that these transitions must exist because D0 and D10 ions are not always colorless, as they should be if there are only dd transitions allowed. So here are a few examples that illustrate this. So for instance, the zinc 2 plus ion is a D10 ion. So in a D10 ion, well, all the d orbitals are being full, therefore you shouldn't have any dd transitions. So therefore, well, any zinc salt, zinc 2 plus salt, should actually be white. And that is in accordance to observation. So now let's look at the copper complex, such as tetraacetonitrilo copper 2+, which contains a copper ion. So now our copper ion is also a D10 ion. Okay, and again, one would expect, therefore, that the respective complex is colorless. And in this case, it is actually really colorless, as we would expect. So, however, if you exchange the ligand and go from a acetonitrile ligand to a phenanthine ligand, then despite our expectation that our complex should be colorless, because again we have a copper 1 ion, our complex is surprisingly dark orange. Okay? So that dark orange color now cannot be explained by DD transitions. So what is the reason for that color? So here are just a few more examples. So titanium tetrafluoride. You have titanium in the oxidation state +4. In the oxidation state +4, it's a D0 ion. So also in D0 ion, you shouldn't have any electron transitions in d orbitals or social terms. So we should have colorless or white color. So this is indeed what we observe. The same for titanium tetrachloride. We also have a colorless substance, but for titanium tetrabromide, we have an orange color, despite we have a D0 ion. And for titanium tetraiodide, we also have a D0 ion, which is colorful. In this case, our substance has a dark brown color. Again, we cannot explain this by assuming DD electron transition because we don't have any D electrons. So here are two other examples. So you all probably know that the permanganate ion is very deeply purple. Okay. But the manganese is in the oxidation state +7. So it's a D0 ion. So why actually is permanganate so deeply colored, given that we do not even have any D electrons available? The same with dichromate. You all know that this is bright orange, but the chroma in the oxidation state +6. In the oxidation state +6, the chromium is a D0 ion, and therefore we do not have any color expected. Okay, but we measure bright orange color. So now, how can we explain this? We can explain this by so-called charge transfer transitions. So here's a very simplified generic molecular orbital diagram of a complex, which is assumed to be octahedral here. So certainly we would have the T2G and the EG molecular orbitals to consider, and we could have DD transitions in between them. But below these, we can have pi molecular orbitals, which are mostly at the ligands, coming from pi donor interactions between the metal and the ligand. And we can also have sigma molecular orbitals coming from the sigma interactions between the metal and the ligand. So in addition to that, above the d orbitals, we can have pi star orbitals, which are mostly at the located mostly at the ligand, and they come from the pi, can come from pi acceptor interactions between metal and the ligand. So now, of course, it is also possible that we can have electron transitions from these sigma MOs and these pi MOs into metal d orbitals. Okay. So now, because these molecular orbitals here are located mostly at the ligand, and the metal d orbitals are located mostly at the metal, we can call these transitions ligand to metal charge transfer transition, because as the transition occurs, charge density is being transferred from the ligand to the metal. And these transitions can be in the visible range if just the energy difference between the metal orbitals, okay, and these bonding molecular orbitals is just small enough so that, well, the electron transition occurs within the visible range. Okay? And we can talk in a moment under which circumstances this is actually the case. So vice versa, we can also have the case that we have metal d electrons that get excited from the metal T2G or EG orbitals into interbonding pi star orbitals, which are also located mostly at the ligand. So in this case, we will have electron transfer from these MOs, which are mostly at the metal, to these pi star MOs, which are mostly at the ligand. So therefore, we can call these transitions metal to ligand charge transfer transitions. And again, if the energy difference between the respective orbits is just small enough, then these electron transitions can occur in the visible range, meaning visible light can be absorbed in order to make these electron transitions happen. So now, under which circumstances can we expect a ligand to metal charge transfer transition in the visible range? And under which circumstances can we expect a metal to ligand charge transfer transition? Yeah. So I forgot one thing, which is that usually these charge transfer transitions are both spin and Laporte allowed. And for that reason, if they occur, the associated color is usually very intense. So that explains, for instance, the very deep color of the permanganate anion and the very bright orange color of the dichromate anion. Okay, but now to the question, under which circumstances are these transitions in the visible range? Yeah, and I forgot one thing to explain. How can you identify and distinguish charge transfer transitions from metal DD transition? So one way to distinguish them, which is very easy, is to dissolve the respective substances in different solvents. And then often different colors are being observed in different solvents because charge transfer transitions are often solvatochromic. And that is plausible because the ligands are in contact with the solvent, and there are also electron-electron interactions between these ligands and the solvent, which influences somewhat the electronic structure and the exact energy of the ligand orbitals, so that basically these energies here are affected by the solvent a little bit, and also the energy of the pi star MOs are affected a little bit. Not so much the T2G and the EG metal orbitals, because the metal is located at the center of the complex, which is not directly intact with the solvent. Okay, but now let's really look at the question: what promotes ligand to metal charge transfer transitions and metal to ligand charge transfer transitions within the visible range. Let's first look at the ligand to metal charge transfer transitions. Okay, so both certain properties of the metal and certain properties of the ligand help this kind of transition to occur in the visible range. So for the metal, we would like that the valence orbitals have actually a low energy. Okay, and that is the case when they have a high positive charge. Okay, or when the metal has a high positive charge, because then the metal draws the electrons in the valence orbitals more strongly to itself, which decreases the energy of the metal valence orbitals. Okay. In addition to that, it is ideal when we have few or even no d electrons, because electron repulsion tends to increase the energy of the metal valence orbitals. Okay, so of course this is, for instance, the case for manganese 7, chromium 6, or titanium 4. Okay, they all have a quite high positive charge, and they are all d0 ions, so they have no d electrons. All these factors actually lower the energy of the valence orbitals. So now, what about the ligand? So for the ligand, favorable properties are that the ligand MOs are having a high energy. Okay, so why is this? Well, we can briefly go back to the previous slide, and our task is actually to minimize the energy difference between the metal orbitals and the ligand orbitals here. So we can do this by lowering the energy of these orbitals and by increasing the energy of these orbitals. Okay, we have thus far discussed the metal d orbitals. Now let us look at these molecular orbitals, which are located mostly at the ligand. Okay, so now under which circumstances tend the ligand MOs to be high? Well, that's the case when we have typical pi donors, and that's the case when we have negatively charged ligands. Because when we have negatively charged ligands, then we have more electron repulsion, and that increases the energy of these the respective orbits. And you see that this is, for instance, the case for O2 minus, where we have pi donor electrons and we have a negative charge at the ligand. That's the same is true for chloride, bromide, and iodide, for instance. Okay, so with this, we understand why the permanganate has such a deep, dark purple color due to a ligand to metal charge transfer transition. The manganese in the oxidations +7, hence its valence orbitals have a low energy and has O2 minus anions as the ligand, which are pi donors and have a negative charge. Therefore, the respective pi molecular orbitals have a high energy, so that the energy difference between these orbitals and these orbitals is small enough so that light absorption in the visible occurs. And this light absorption is both spin and Laporte allowed. Therefore, we see it in a very high intensity, which gives the permanganate ion its very deep color. So now, what about the metal to ligand charge transfer transitions? So now here, we want to minimize the energy between the metal d orbitals and the pi star orbitals. So what minimizes this energy? We can first look again at the metal ion properties. So in this case, we want to have the energies of the metal d orbitals as high as possible. So that can happen when you have a low charge at the metal. And when we have many d electrons in the metal, because then we have strong electron-electron repulsion, both increases the energy of the metal d electrons. So examples for that are, for instance, copper 1, which is a d ion. Okay, so now what about the ligand properties? So in this case, we want to lower the energy of the pi star orbitals as much as possible. So what is helpful for that? Well, it is helpful when we have a pi acceptor ligand with low-lying pi star orbitals as the ligand. So that's, for instance, phenanthroline, cyanide, carbonyl, and thiocyanate ligands. So they both have low-lying pi star orbitals that can interact with the metal d orbitals, which have a relatively, they do not interact, but they are close in energy, relatively close in energy to the metal d orbitals, so that electron transitions can occur. Okay, so this explains, for instance, the intense dark orange color of this copper 1 phenanthroline complex. So our copper ion is a D10 ion, which has a lot of electrons with a low charge at the metal. And we have a ligand, which is a strong pi acceptor ligand, which lowers the energy of the pi star orbitals. All right. So also this complex has spin allowed and Laporte allowed metal to ligand charge transfer transition. So for that reason, the color is again quite intense. All right, so now we are finished with our chapter on electronic spectra. So our time is pretty much over, so I don't think I want to start a new chapter at this point. So we can just stop the recording here.